Hello and welcome to our 20th lecture, Combinatorics. So today we will learn how to count without having to list out everything we're counting first. Let's jump right to the fundamentals of counting principle. Let's say we have two actions. Action 1 can happen in A number of ways, and action 2 can happen in B number of ways. For example, action 1 is dropping a ball, and it can either bounce on the floor or on the chair. This is two ways. Action 2 would be picking up the ball, either with our hand or foot. So we have two ways again. If I were to draw it out, in the horizontal top row, I would have action 1 marked with both of the ways, and in the vertical column, I would have action 2 options, so hand or foot. To see how many actions are possible for such an example, we pair each with each. Like the square I have here, we have all 4 possible combinations because 2 and 2. Hand from chair, hand from floor, foot from chair, and foot from floor. So we see that we multiplied together the numbers of ways to get the number of how many possible combinations we can make with these. So let's see this on a more everyday example, like dressing up in the morning, for instance. Our first action would be having a shirt, and second action would be having pants. We have three different shirts, 3 different ways to have one, and we have 4 different pants, so 4 ways of pants. That doesn't sound any better. So let's find all the combinations between the shirts and pants, like all possible combinations you could have. We would pair each with each. So for first shirt, we would have 4 combinations, so 1 with each pair of pants. Then second shirt would have 4 again, and third shirt would have 4 as well. That adds up to 12. Or in other words, 3 times 4 is 12. It is the formula for all the combinations we can have here. So basically for each element in the result, whether it's a password combination, a dress combination from separate clothing articles, you multiply together all possible options or ways for the option to happen for each part. So let's see how this applies to something more complex, like password, for instance, which we know starts with 2 letters and ends with 3 digits in this exact order. How many possible passwords could we make if we count that capitalized and uncapitalized letters are treated as the same letter? So capital A and lowercase a are the same in this example. Well, let's write it out. Since we're assuming an English alphabet, we have 26 options for each letter and 10 options for each digit. Now we just have to... So now that we have determined the number of options we have at each position, we can solve for the count. We had first our 2 letters, so for each position of the letter we would have 26 times 26, and then for the 3 digits we have 3 places here, and we insert 10 for each, so from 0 to 9. We multiply all these together and we get 676,000 possible passwords. That's why they recommend setting up longer passwords, because if the hacker tried to brute force their way into it, they need to search longer. This is actually a very low number, because if we really wanted to guess a random password that only has 5 places, we would have a lot more options, because there's not just 2 letters and 3 digits and everything. We would have to add them all up together. For homework, try to calculate how many. So treat that there's a 5 symbol long password with either letters or digits. So you have to add them all together. You don't have to account for special symbols, just to see how many possible passwords you can actually make if you just know that there's letters and numbers in the password. So yeah, a little hint, here we specified which place was occupied by which symbol. In the homework, you just have to know that either of these 2 symbols can appear. And instantly it goes 36 times 36 times 36 times 36 times 36. You just plug that together and see how many actual numbers there are. Or sorry, possible passwords there are. Next up, we move to factorial notation. You may be wondering, what the hell is a factorial? And my answer would be very loud. As you can see here, this example is obviously 120 because we know that multiplication comes first, so you subtract and you get 120. But why is this funny? Because if you subtract first and then multiply by 0.5, you would get 5 as the answer. So technically, the confidently wrong answer shouted became correct due to a factorial notation, the exclamation mark. Factorials are basically multiplying all natural numbers up to the number itself together. So n factorial is marked with n exclamation mark, and it equals to n times n minus 1 times n minus 2 etc., times 2 times 1. So let's have following examples to show how this works. 1 factorial is 1. 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. As you can see, the result increases very fast. You can say it goes even faster than exponential in many cases. There is a special case, however, and that is for 0 factorial. It equals 1. Why? For proof, we can just rewrite n factorial as n times n minus 1 factorial, which we can do since n minus 1 factorial just means this right part here, and we just separated this away. This is a very handy property we will use later, but here let's set n as 1. So 1 factorial is 1 times 1 minus 1. And we simplify it, so we have 1 factorial equals to 1, 1 factorial equals to 1, and 1 minus 1 equals to 0. And since we don't know the value of this, let's solve for it. We have 1 that 1 times something is something, so this cancels out, and that's basically it. Very easy, nothing flashy proof. There is some other factorial notations. I make a short video as fun facts and stuff, but they're not as commonly used for you to need to know them, but they're just fun to know. So why are we covering this today, and why did we cover counting first? Well, if we draw connections to the previous topic, we know if we multiply all options together, we can get all possible combinations, right? And factorial deals with multiplication, however, the numbers in it are decreasing with each next number. So hopefully some of you can see where we're going with this. And it's a way to write out how to arrange n different objects. Important part, different. Well, for this part, any objects are fine, but later on different becomes important. Since every time you put one object from the set down into the order, you have one object less in the set, so the n in the set is decreasing. Let's say we have 3 marbles in the set. These marbles are colored differently, which is very important. I will mark the set with a white outline, shaped like a bag, and our marbles are red, blue, and yellow. How many different ways could we order them in? Well, we have 3 positions that are possible, since we're using all 3 marbles to place them in a certain order. Our first position can have either of the 3, so we write down 3. And let's say that we decided that red will be placed first, leaving us with 2 marbles left. Either of them can take the second place in this order, so we have 2 options, so we will multiply the 3 before to 2. Let's decide we leave the blue marble at the second position, leaving me with only 1 last marble, the yellow one, as the only option for the last place, which is 1, so we multiply by 1. So when we multiply the numbers together, we get 6, which is all possible ways in which we can order the 3 colors, which are all listed here. You could also say I have listed all the permutations. We could show the same example with seats, like having 4 students and 4 chairs, and when one chooses a chair, there's 1 less left to fill. So what even is a permutation? It is a selection in which order matters. To be more clear, it is a selection of different elements in which the order matters, meaning red, blue, yellow is not the same as blue, red, and yellow. We mark permutations as P and K, like so. This symbol will mark the number of all permutations, so the count, or number of sets where the order of different elements matters. N labels number of all objects we have. For instance, if we have 5 marbles, 4 people, 2 shirts, 7 pens, or however many stuff. K marks the numbers of positions filled, so 3 pedestals for marbles, 3 chairs for 4 people, 1 pencil case with 5 pen spots for 5 out of 7 pens, etc. So essentially positions in the permutations that are filled. Now, since this is math, of course, there will be a formula for it. We take the factorial of the number of objects that we have and divide it by the factorial of the number of objects that haven't been used in positions filling. So objects minus positions filled. There is another way to write the symbol, and that is by putting the number of objects in the superscript before the P, and K, so the number of positions filled or objects chosen, whichever you choose to remember, is in subscript on the right after P. I will be using the brackets writing as it is a lot easier to do it on PowerPoint without being messed up every time I duplicate a slide. So our example states we have 5 students and 3 chairs. We want to see how many possible scenarios or permutations do we have for the order of 3 out of 5 students. So what's our n and k? Well, n is all the objects that we can work with, so here these are students. K is for the number of positions that can be filled, so here k will be 3 for 3 chairs. So let's put them in and have our formula set and just insert the numbers in. So 5 minus 3 is 2, so we will have 2 factorial. 2 factorial is 2 times 1, so let's just write this all out in the open. So 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. We can cancel out the 2's and 1's, obviously, and we're left with 5 times 4 times 3, which is 20 times 3, which is 60. So if we have 5 students, there is exactly 60 different ways to order them on a set of 3 chairs. Very useful, right? Well, actually it is. And we will probably see that in the next lesson. I think. I forgot what the next lesson is. I think it's probability. Anyway, time for combinations. This is a selection where the order does not matter. The mark here is similar to permutations, except we use C instead of P. As for the formula, it has a symbol the same way permutations did. However, this formula has an extra part. And that is that it's also divided by the number of places where the objects are set, factorialized. Yeah. But yes, since the order here does not matter, ABC and CBA would be treated as the same combination, but 2 different permutations. So what we see is that the 2 numbers in the denominator before they're factorialized, they add up to n. So k plus n minus k is n. So this is a fun property we can observe. Useful later on. We divide the factorial of the number of all elements we can work with the factorial of the amount of positions in which we can set them, and then divide the result again with the factorial of all the elements that were used. We could also get the number of combinations if we calculated all permutations, so where the order matters, and then divide that amount that we get with the amount of all the possible ways to arrange the chosen items, so all the possible permutations, which equals to k factorial, so permutations of all the objects in the ordered set. There is an amazing video, roughly 7 minutes long, which explains it super well. It was made by David Dobrovich, titled Derive the Combinations Formula. Anyway, let's get ahead and actually solve an example. I think I have a good explanation coming up later as well. So here we have 5 students, and you as the teacher must pick 3 for a group project on something. How many possible combinations could you possibly make, since a group like this does not care for the order in which you pick them? Let's insert the numbers in. We simplify the bracket here. We write out the factorials, and we get a mess like this, so let's start simplifying the fraction. I will cancel out the 3 factorial on the left, so this one with the top part, and this will leave us with 5 times 4 divided by 2 factorial. We can cancel out the 4 with the 2, leaving us 5 times 2 on top, leaving us with 10. There is a total of 10 possible combinations for such a group. So now we know we use combinations every time where only membership matters, not the order of members in the set. So where you would have permutations for stuff like podium winners, you would have combinations for team selection. There is the third way to count, and that is called variations. Much like permutations, the order matters. However, it differs from them in one important aspect. Permutations are for items that are different, like people, different colored marbles, fabrics, etc., where variations are when you have indistinguishable items such as marbles, where there's like 3 yellow and 4 blue, or notebooks, mass-printed notebooks for a certain class, or a textbook in which from which you can learn it and you don't like take notes in it. So if you would take one at random, you couldn't be certain which exact one it is. So basically, permutations where order matters and all objects are different, combinations where order does not matter, and variations where order matters and elements can be identical are the 3 main points of today's lesson. But I'm not gonna be bothering you with variations because it's hard to explain it well, and the formula is simple to permutations, and it's very confusing. And if you really want to know them, I recommend reading up on your own, because if you're just listening to me yapping here, it's not gonna help. Unfortunately, that's the truth. So for our first example, we have 6 students and 4 possible different topics to choose from to make a presentation. The topics are not exclusive, meaning that multiple students can do the same topic, but they must do their separate presentations. The question here is, how many possible presentations are there to be made? To solve this, we first think what the example wants from us. So presentations are when a student chooses a topic and makes a presentation in front of the class. So for all possible presentations, we need to count all possibilities. In this case, the 4 possible topics each student could choose. So 4 choices per one person, 6 students, 6 people, gives us 6 times 4. Our possible presentation count, or PP, equals to 6 times 4, which is 24. Simple, right? Someone smart once said that something along the lines of, if you write the problem down clearly, then the matter is half solved. As especially here, if you know what you need to solve for and write out all the information you have, you only need the right formula. And even then, you can wing the calculations as you go, as long as you know the right fundamentals. And the fundamentals are what I try to present for you to at least try to understand or be familiar with. For our second example, we're asked how many possible podium results can we get in a competition with 8 runners. So let's think. Podium has 3 spots. It is known as the order of players, competitors, of how good they were. So the order does matter here. So we need permutations, aka possible assortments of runners in a certain but important order. So even if we forget the formula, we know that the number for all possible orders of 8 runners at the end of the race is 8 factorial, as in all possible results of a race. Now, since we only need to know for first 3 places, we will take the first 3 parts, terms, in the factorial. Well, I guess the term isn't really correct, since they're separated by addition and subtraction to be terms, but here I'll use it since it's kind of helping explain the point. But yeah, we draw the lines for each podium place. In first place, there can be either of the 8 runners, so we have 8. In the second place, it can be either of the 7 remaining runners, and in the third place, either of the 6 remaining runners. And when we multiply that together, we have 336 possible permutations or podium options, and that just for 8 runners. Fascinating, isn't it? And for our third example, we need to build a committee out of 10 candidates. How many possible committees could you build? This example is asking us for different committees, and since committees like this don't usually care about the numerical order of members, we just need different groups, which are combinations. So we have 10 factorial for all the possible orders of 10 people in 10 places. Now we need to have that set into 4 spots, so we divide by 10 minus 4 factorial, which is 6 factorial. And since this formula we have right now would give us the number of committees where the order matters, which we don't want here, how do we reduce it? Well, by dividing by all the possible ways we could order the members in this committee, so within the 4 spots of the committee. So all the permutations of 4 possible people in a 4-person group, basically 4 factorial. And that's 210 possible committees. So one way to remember how combinations work is by thinking of factorials as always existing in a form of fraction. So a factorial of some number, so like 8 factorial, is always divided by a factorial of another number, which is as a unit of is adding an extra variable named order. So let's say we have 8 factorial, 8 people. If we arrange them in a line with 8 spaces, permutation formula would tell us 8 factorial on top and 8 minus 8 factorial on the bottom, which ends up as 1 on the bottom. So technically, now this is one way you can understand this. This is in no way the correct explanation, but this exclamation point is always present as a fraction, most commonly as 1 factorial underneath it. When this form is written, it stands for order, so it dictates a certain order to the set that you're building. So for combinations, I found it helpful to explain it to myself that you're dividing by another order. So a mock formula could look something like this, where the number of combinations is the permutations of the example divided by the permutations in the smaller set. So the permutations of the whole thing is how many ordered sets exist for the size of the set, but to get the combinations, you divide it by all possible orders in the smaller set. It's very overcomplicated, but basically you're dividing with the second permutation to get rid of the order component, kind of. Either that, or you're removing all the ordered components in the specific subset. Basically, like we had square root of -1 was I. Here, factorial divided by factorial equals order. It doesn't cancel out the factorials, it just equals order. And two orders do cancel out if they're put in a fraction, so a double fraction would cancel out the orders, giving us combinations. As you can clearly see here, k minus k is 0, because they're equal. This is 1, so if we divide this by this, we get the formula for combinations. I hope this was a clear and helpful way for you to like understand how combinations could work and why they work the way they do. Now, since we have mastered combinations, we can now learn a symbol that describes the formula in a shorter way. It's called a binomial coefficient. It is a bracket with n written on top and k on bottom, just like in a fraction, however, there is no fraction line. It basically means the number of ways of picking k unordered outcomes from n possibilities. This notation will be very useful, important later on, and it's very handy as well. It basically means this. This is the formula for combinations. So from this formula and this notation, we can derive a couple of properties. The first identity or the property or the rule is logical from the formula, since the quote-unquote denominator the denominator in the formula contains two numbers that sum up to 1 in the numerator. If we ignore factorials, of course, it makes sense that the binomial of n over k, so let's have an example, 7 over 3, in this example, would also equal a binomial 7 over 4, because you could just mark this bracket as k, and this one as n minus k, because the equality stands. 7 minus 4 is 3, and 7 minus 3 is 4. So we have this writing that n over k in a binomial symbol like this equals to n over n minus k. Very handy, I forgot why, but when math gets more complex, this is useful. So I'm not gonna go too much into it, but from this we can get another property that if k is 0, then n over n0 and n over n must be equal, because n minus 0 is n. But why do I point it out? Because there's another thing that this equals to, and that is 1. Because if you insert 0 here and n here, you would have 1 factorial times n factorial in the denominator in the fraction, and n factorial on top, and n factorial and n factorial would cancel out, and giving us 1. These are just two main identities I point out. There's a lot of other ones. There's like hyperfactorials, but I'm presenting this just as a short intro for future lessons and future updates. So in summary, when we're asked about counts, as in two events or objects that are in some way connected, we're counting the connections. For connections, we have to multiply the choices. So like you could draw out dots and connect each dot to each another dot. So like, let's say, back to our original example, hand, foot, and chair, floor, we could make connections between the dots for hand, and then connections between the dots for foot, and there would be 4 total connections, like 4 lines between the left and the right. That would be one way of visualizing it. Actually, can I draw this? Yeah, I can. Like, let's say this is option 10. So we have one option here, another option here. These are for option 1. These are 2 possible ways it can happen. So way A and way B. Okay? And there's option 2, which can happen in, let's give an asterisk to make it more clear, in this way and this way. Now, this one can happen with this or with this, and this one can happen with this or with this. Now, if we go straight down, I don't recommend going down the middle. If we go straight down and count all the lines we intersect, so one line, second, third, fourth, it adds up to 4. So this is another way of doing it visually. But with more numbers, it gets a lot more confusing. For instance, magic circles, you have like a pentagon where each is connected to others. Same way you would derive the diagonals in like the shapes, etc. But yeah, you would just count all the connections between the points. This is a very poor example because you cannot occur the floor and the chair at the same time, so these would not matter. There's a special formula for shapes for this as well. I could do a video on it, but it's not important right now. If you want me to make a video on like how to count the diagonals in the shapes, like polygons, etc., do comment down below, because I generally would make the video on that, and it's something very interesting as well. But yeah, that's for that. Next is factorial, an exclamation mark, which is an operation that means the product of all natural numbers from 1 to n. Factorial is so like 1 times 2 times 3 times 4 times 5, etc., etc., and is used when counting possible orders where the items are consumed or taken away from the original set, so we cannot use them in the order anymore. Permutations are basically arrangements where order matters for different items. Combinations are arrangements where the order doesn't matter, like an ice cream combination like strawberry and chocolate or something that you may like. It doesn't matter which one is first or last, as long as you get both, you're happy with it. There's also variations where the order matters, but the items can be the same or identical. And finally, to differentiate between the everything, ask yourself, if you swap 2 items in the made set, would there be a difference between the original and the swapped set according to the task at hand? And if the 2 items are different, so does a change in positions change the outcome? That's one way you can ask yourself to help you solve the problems. So here is the mini test after today's actually short lesson. That's crazy. I wish you best of luck. The first one was a bit tricky because I forgot how to solve it. But yeah, in the mini test solving, I solved it correctly. I hope, you'll see. The second one is a very random one. I finally gave into the brain rot, and there's a third one, very simple. And this is it for today's video. I hope everyone enjoyed, well, as much as you can enjoy math. Thank you so much for tuning in. I appreciate all of you, and I'll actually, I may stream on Tuesday with a friend of mine. We're gonna play Lethal Company, very probably. I may stream later as well, so do comment down below, stay tuned. I'm gonna be streaming on Twitch. Maybe if I can manage, I'm gonna set up a multi-stream towards YouTube as well. Yeah, that's it. There's a Minecraft video coming hopefully soon. I'm still editing that summer collab with Among Us we had. There's like a lot of videos and it keeps crashing, so I'm gonna figure something out, don't worry. This year is gonna go out with a bang. But yeah, thank you so much for tuning in. And I'll see you all on our next quest. Bye!